For instance, when you do the experiment to measure the damping of a plate, for example, and when you hit it, then you can measure this, right? By recording the displacement, and you can measure RD. But that is not essentially the whole mechanism that loses energy by the plate. The plate also loses energy due to radiated sound. Right? So if you measure, if you try to measure RD by measuring sound pressure, for example, okay, that might not be this RD, but including radiated, the damping effect due to radiation. So you have to be very careful to measure RD, okay? Especially when the structure has a very small RD. The radiation due to sound energy is no longer negligible, okay? Anyway, I will go back the picture I made over here. Okay. Therefore, what I can say is that due to the radiation in both sides, the reason why I have 2 is because this is radiated in both sides. Okay. Then, can we get tau due to this kind of general partition? Based on this observation, we can say that, oh, there should be 2Z0 and 2Z0, and then the contribution due to partition would be composed by 3 components. One is to the motion of mass, j omega m, and the other one is due to the motion, due to spring. And if I denote spring constant S, then I can write this would be S divided by m or multiply by m or m square. Okay, J is indicates the phase relation with velocity, right? Because this is the related with RD, and 2Z, there's no J or -1, means that we are considering this term what is in phase with velocity. That's what we can guess, right? But the stiffness has phase that is minus j omega, that has effect of minus j omega, right? 1 over minus j omega, in fact. So remember the phase diagram. This is the displacement, and this is the velocity, and this is inertia, and this is excitation force, right? And the phase relation between this and this is what? I have to rotate this way, therefore I have minus j omega factor. So I can write over here j omega minus. And I can write over here RD. Okay? Or I can generalize this concept by writing like this. Tau that has Z partition impedance and fluid loading impedance and fluid loading impedance. And in this case, fluid loading impedance is 2Z0. Fluid loading impedance, in other words, the impedance that has to do with the vibration of partition. Okay? So this is what we can expect. Let us, whether or not this gas can be obtained by looking at the physics associated with this problem. Okay? So I explain. Mm-hmm. This one is minus? This one? Oh yeah, sorry. And this is plus? This is minus? Plus? Plus? Okay. Yi-Gi-Hoon, you understand? You are studying even though you are even though when you sleep, right? Okay, so let's confirm what we have by looking at the problem of this. Okay. First, the boundary condition says that the velocity of the fluid particle over here has to be same as the velocity of this partition, and the velocity of this fluid particle over here is same as the velocity of this partition. That is the one boundary condition. Okay? So, let me write velocity at x equals 0 minus has to be same as velocity of the partition that has to be same as the velocity of fluid particle at x0 plus. Okay? What is the velocity over here of the fluid particle over here? That is pi exponential minus j omega t. I put x equals 0 over here. That is the pressure due to incident wave, and divided by rho 0 c. That is the velocity of incident wave, right? Because we are handling plane wave, therefore the impedance is rho 0 c. And the velocity reflected wave can be obtained similarly, but that has to be minus because obviously physically the velocity of the reflected wave toward the negative x-axis. Okay?